Hello everyone. It's been a bit of time since my last live stream. I was in the wrong channel. It's been a bit of time. What is this? Okay. It's been a bit of time since my last. Where's my last live? Yeah, a week ago. I was hosting some reading groups, and yeah, why am I not streaming as much? Well, one is I think reading papers is great, but I feel like I'm starting to read too much and not do enough. And this is why today I just want to follow Karpathy's video on Transformers, because I realized, when looking at, I was presenting Pi Zero, and when I was explaining sort of like this attention mechanism, and I was referring to my diagram on Transformers, I think like this multi-head attention part I'm still not fully familiar with, and also I did not finish with the MLP part, and then I also have not written this in code. So we're going to just, let me go to my GitHub. And let me pull up a repo that I use to program. Okay, I think I have a repo. I guess we're gonna use cursor. No, that's not the right. So yeah, I think I was going through it, and we have this. Okay, wait.
Really all that's required is a proficiency in Python and some basic understanding of calculus and statistics. And it would help if you also see my previous videos on the same YouTube channel, in particular my Make More series, where I define smaller and simpler neural network language models, so multi-level perceptrons and so on. It really introduces the language modeling framework. And then here in this video, we're going to focus on the transformer neural network itself. Okay, so I created a new Google Colab Jupyter notebook here. And this will allow me to later easily share this code that we're going to develop together with you, so you can follow along. So this will be in the video description later. Now,
Is this already done? So we need to build out GPT, and then there's GPT-2, right?
hi everyone. Tokens.
Hi everyone. So today we are going to be continuing our Zero to Hero series. And
now here I've just done some preliminaries. I downloaded the dataset, the Tiny Shakespeare dataset at this URL, and you can see that it's about a 1 megabyte file. Then here I opened the input.txt file and just read in all the text of the string, and we see that we are working with 1 million characters roughly. And the first 1,000 characters, if we just print them out,
Where is this from?
are basically what you would expect. This is the first 1,000 characters of the tiny Shakespeare.
Okay, so we need to just reading a file is not too important. So we're gonna do now text contains Shakespeare and okay, and then this is just tokenizing it. This is easy. We don't need to cards.
Your data set roughly to here. So far so good. Next, we're going to take this text, and the text is a sequence of characters in Python. So when I call the set constructor on it, I'm just going to get the set of all the characters that occur in this text. And then I call list on that to create a list of those characters instead of just a set, so that I have an arbitrary ordering. And then I sort that. So basically we get just all the characters that occur in the entire data set, and they're sorted. Now the number of them is going to be our vocabulary size. These are the possible elements of our sequences. And we see that when I print here the characters, there's 65 of them in total. There's a space character, and then all kinds of special characters, and then capitals and lowercase letters. So that's our vocabulary, and that's the sort of like possible characters that the model can see or emit. Okay, so next we would like to develop some strategy to tokenize the input text. Now, when people say tokenize, they mean convert the raw text as a string to some sequence of integers according to some vocabulary of possible elements. So as an example, here we are going to be building a character level language model. So we're simply going to be translating individual characters into integers, etc. Integers and to the but you're not encoding different schema in practice. So for example, Google uses sentence piece. So sentence piece will also encode text into integers, but in a different schema, and using a different vocabulary. And sentence piece is a subword sort of tokenizer. And what that means is that you're not encoding entire words, but you're not also encoding individual characters. It's a subword unit level. And that's usually what's adopted in practice. For example, also, we're going to implement a single, what's called head of self-attention. So this is just one head. There's a hyperparameter involved with these heads, which is the inefficient. Aggregate anything from the 6th node, 7th node, and inputs. So 0 mean unit variance. K and Q are unit Gaussian. Okay, large count. The head size will and unit standard deviation, 1 standard deviation output. So what I did here is I'm copy-pasting the Bachelor 1D that we developed in our MakeMore series. And see here we can initialize, for example, this module, and we can have unit mean. Now the rows are not going to be normalized by default, because we're just normalizing columns. So let's now implement layer norm. It's very complicated, normalized, but the rows are going to be normalized. You see that the add and norm is applied after the transformation. Now it is a bit more basically common to apply the layer norm before the transformation. So there's a reshuffling of the layer norms. So this is called the pre-norm formulation, and that's the one that we're going to implement as well. So slight deviation from the original paper. Basically, we need two layer norms. Layer norm 1 is nn dot layer norm, and we tell it how many, what is the embedding dimension. And we need the second layer norm. And then here, the layer norms are applied immediately on x. So self dot layer norm 1 applied on x, and self dot layer norm 2 applied on x before it goes into self-attention and feed forward. And the size of the layer norm here is n embed, so 32. So when the layer norm is normalizing our features, it is the normalization. And we can also drop out here generating text, and it's unconditioned on anything. We're just blabbering on according to a given dataset. What makes it a decoder is that we are using the triangular mask in our transformer. So it has this autoregressive property where we can just go and sample from it. So the fact that it's using the triangular mask to mask out the attention makes it a decoder, and it can be used for language modeling. Now, the reason that the original paper had an encoder-decoder architecture is because it is a machine translation paper. So it is concerned with a different setting. In particular, it expects some tokens that encode, say, for example, French, and then it is expected to decode the translation in English. So you typically, these here are special tokens. So you are expected to read in this and condition on it. And then you start off the generation with a special token called start. So this is a special new token that you introduce and always place in the beginning. And then the network is expected to output neural networks are awesome, and then a special end token to finish the generation. Bring the etc. But the model.py should look very, very similar to. They trained a number of transformers.
I think we need to do GPT-2.
Hi everyone. So today we are going to be continuing our Zero to Hero series, and in particular, today we are going to reproduce the GPT-2 model, the 124 million version of it. So when OpenAI released GPT-2, this was 2019, and they released it with this blog post. On top of that, they released this paper, and on top of that, they released this code on GitHub, so OpenAI/GPT-2. Now, when we talk about reproducing GPT-2, we have to be careful because in particular in this video, we're going to be reproducing the 124 million parameter model. So the thing to realize is that there's always a mini-series when these are releases are made. So there are the GPT-2 mini-series made up of models at different sizes, and usually the biggest model is called the GPT-2. But basically the reason we do that is because you can put the model sizes on the x-axis of plots like this, and on the y-axis you put a lot of downstream metrics that you're interested in, like translation, summarization, question answering, and so on, and you can chart out these scaling laws. So basically as the model size increases, you're getting better and better at downstream metrics. And so in particular for GPT-2, if we scroll down in the paper, there are 4 models in the GPT-2 mini-series, starting at 124 million all the way up to 1558 million. Now, the reason my numbers, the way I say them, disagree with this table is that this table is wrong. If you actually go to the GPT-2 GitHub repo, they sort of say that there was an error in how they added up the parameters, but basically this is the 124 million parameter model, etc. So the 124 million parameter had 12 layers in the transformer, and it had 768 channels in the transformer, 768 dimensions. And I'm going to be assuming some familiarity with what these terms mean, because I covered all of this in my previous video, Let's Build GPT-2, Let's Build GPT from scratch. So I covered that in the previous video in this playlist. Now, if we do everything correctly and everything works out well, by the end of this video, we're going to see something like this, where we're looking at the validation loss, which basically measures how good we are at predicting the next token in a sequence on some validation data that the model has not seen.
Let's go over this code first, and maybe he doesn't need to explain to us. So we split it into train and val. We understand this, and we then treat. So x is the train data up until the block size. You take the first 8. Okay. I guess it's an example of context and target, right? Like, oh, so 1D vector of this size, and then we see the first 1,000 tokens, which we've tokenized by encoding the text. And we look at our trained data, block size. Not sure what they mean by block size actually.
Trained a number of transformers for any arbitrary split, block size of 8. And the context is always all the... Okay, so now we would like to start out of the training set and train on just chunks at a time. And these chunks have basically some kind of a length and some maximum length. Now, the maximum length typically, at least in the code I usually write, is called block size. You can find it under different names like context length or something like that. Let's start with the block size adjust.
Okay, this is the maximum length. Okay, the context length. Okay, got it. So the train data is the context length, and then you're predicting the next target, which is the token right after. Alright, so this is where it gets confusing, right? It's like you actually predicted like one shifted.
And let me look at the first train data characters. This actually has multiple. I actually generate batch size number of random offsets. So because this is 4, ix is going to be a 4 numbers that are randomly generated between 0 and len of data minus block size. So it's just random offsets into the training set. And then x's, as I explained, are the first block size characters starting at I. The y's are the offset by 1 of that, so just add +1. And then we're going to get those chunks for every one of integers. So I'm just run it, it's block size characters, so it's offset by 1. And that's because y are the targets for each position in the input. And then here I'm iterating over all the block size of 8. And the context is always all the characters in x up to t and including t.
including t plus 1.
And the target is always the tth character, but in the target's array y. So let me just run this. And basically it spells out what I said in words. These are the 8 examples hidden in a chunk of 9 characters that we sampled from the training set. I want to mention one more thing. We train on all the 8 examples here with context between 1 all the way up to context of block size. And we train on that not just for computational reasons because we happen to have the sequence already or something like that. It's not just done for efficiency. It's also done to make the transformer network be used to seeing contexts all the way from as little as 1 all the way to block size. And we'd like the transformer to be used to seeing everything in between. And that's going to be useful later during inference, because while we're sampling, we can start the sampling generation with as little as 1 character of context. And the transformer knows how to predict next character with all the way up to just context of 1. And so then it can predict everything up to block size. And after block size, we have to start truncating, because the transformer will never receive more than block size inputs when it's predicting the next character. Okay, so we've looked at the time dimension of the tensors that are going to be feeding into the transformer. There's one more dimension to care about, and that is the batch dimension. And train on just
important.
chunks at a time. And these chunks have basically some kind of a length, and that's find it on the different names. First one is we're going to characters out of the characters. I'll explain. Start with the block size of just 8. And let me look at the first train data characters. The first block size plus 1 characters. I'll explain why plus 1 in a second. So this is the first 9 characters in the sequence, in the training set. Now what I'd like to point out is that when you sample a chunk of data like this, so say these 9 characters out of the training set, this actually has multiple examples packed into it. And that's because all of these characters follow each other. And so what this thing is going to say when we plug it into a transformer is we're going to actually simultaneously train it to make prediction at every one of these positions. Now, in a chunk of 9 characters, there's actually 8 individual examples packed in there. So there's the example that when in the context of 18, 47 likely comes next. In the context of 18 and 47, 56 comes next. In the context of 18, 47, 56, 57 can come next, and so on. So that's the 8 individual examples. Let me actually spell it out with code. So here's a chunk of code to illustrate. X are the inputs to the transformer. It will just be the first block size characters. Y will be the next block size characters, so it's offset by 1. And that's because Y are the targets for each position in the input. And then here I'm iterating over all the block size of 8. And the context is always all the characters in X up to T and including T. And the target is always the tth character, but in the target's array Y. So let me just run this. And basically it spells out what I said in words. These are the 8 examples hidden in one of that. So just add plus 1. And then we're going to get those chunks for every one.
So there are many examples packed into the same. And you use the full context length because it's much more effective at storing. I mean, you just get to pack multiple examples. And the way practically this works is when you go through your attention matrix, right? Like these tokens, like it's L by L, and I guess that part is not super clear to me. So let's go down into the code and we'll see how it actually gets used. So we set a batch, and this is exactly what Karpathy said. We get a batch, inputs and shape, and so your targets are the same, but just offset by 1. So it's batch size by context length, and we need to learn optimizer. Okay. Why do we have a diagram model here? Okay, I guess the language model. Okay. Create an embedding table, and then you get the logits, and this is there's a hidden dim somewhere, right? Where you're making the hidden
One
image
of
the
integers
same
I.
as the Lucas?
Okay, so now that we have
positions here. So I haven't, but here when we go to the documentation, do that because currently the tokens are not talking to each other and they're not seeing any context except for they're just seeing themselves. So I'm a token number 5, and then I can actually make pretty decent predictions about what comes next just by knowing that I'm token 5, because some characters follow other characters in different scenarios. So we saw a lot of this in a lot more depth in the Make More series, and here if I just run this, then we currently get the predictions, the scores.
That's the bag model. Yeah, so they make the embedded dimension the same as the vocab sets. Okay. And then if targets is on, and then you do cross entropy, you just use your current token. The mathematical trick is, forgot this trick. Is there like, they not do multi-head?
Into the current law. We'll see how we can bring that information back later. For now, what we'd like to do is, for every single batch element independently, for every teeth token in that sequence, we'd like to now calculate the average of all the vectors in all the previous tokens and also at this token. So let's write that out. I have a small snippet here, and it's inefficient. Now the trick is that we can be very, very efficient about doing this using matrix multiplication. So that's the block. So first, let's get some quick preliminaries out of the way. Now, in a sequence, is we basically just do a dot product between the keys and the queries. So my query dot products with all the keys of all the other tokens, and that dot product now becomes way. And so if the key and the query are sort of aligned, they will interact to a very high amount, and then I will get to learn more about that specific token as opposed to any other token in the sequence. So let's implement this now. We're going to implement a single, what's called head of self-attention. So this is just one head. There's a hyperparameter involved with these heads, which is the head size. And then here I'm initializing linear modules, and I'm using bias equals false, so these are just going to apply matrix multiply with some fixed weights. And now let me produce a key and Q. B currently produce a key and a query. So no communication has happened yet. But the communication comes now. All the queries will dot product with all the keys. So basically what we want is we want way now, or we apply this. So in particular, we want to transpose. And so this matrix multiply now will basically do the following. B by T by 16, right? So for every row of 0, and the weighted aggregate from this dot product between the keys and the queries. So this can now run, I can run this, and the weighted aggregation now is a function in a data-dependent manner between the keys and queries of these nodes. So just inspecting what happened here, the way takes on this form. And you see that before way was just a constant, so it was applied in the same way to all the batch elements, but now every single batch elements will have different sort of way to color. Data, so this can way, so they're not zeros, they are now.
Where did you mask it?
Coming from this dot product between the keys and the queries. So this can now run, I can run this, and the weighted aggregation now is a function in a data-dependent manner between the keys and queries of these nodes. So just inspecting what happened here, the way takes on this form. And you see that before weight was just a constant, so it was applied in the same way to all the batch elements. But now every single batch elements will have different sort of weight because every single batch element contains different tokens at different positions, and so this is not data dependent. So when we look at just the 0th row, for example, in the input, these are the weights that came out. And so you can see now that they're not just exactly uniform. And in particular, as an example here for the last row, this was the 8th token. And the 8th token knows what content it has, and it knows at what position it's in. And now the 8th token, based on that, creates a query. Hey, I'm looking for this kind of stuff. I'm a vowel, I'm on the 8th position, I'm looking for any consonants at positions up to 4. And then all the nodes get to emit keys. And maybe one of the channels could be, I am a consonant, and I am in a position up to 4. And that key would have a high number in that specific channel. And that's how the query and the key, when they dot product, they can find each other and create a high affinity. And when they have a high affinity, like say this token, I will end up just this. We're looking at way after this has already happened. Let me erase this operation as well. So let me erase the masking and the softmax just to show you the under the hood internals and how that works. So without the masking and the softmax, way comes out like this, right? This is the outputs of the dot products.
Yeah, exactly.
And these are the raw outputs, and they take on values from negative, 2 to positive 2, etc. So that's the raw interactions and raw affinities between all the nodes. But now, if I'm a 5th node, I will not want to aggregate anything from the 6th node, 7th node, and the 8th node. So actually, we use the upper triangular masking. So those are not allowed to communicate. And now, we actually want to have a nice
You mask it, and then you do a softmax, right? So I think in my Obsidian, I also do Qk. Yeah, I'll probably just draw it. And here I probably just like wanna draw a custom shape. QKT divided by square root of wait, where's the freaking attention? Yeah, I think like it's actually just like it's not like you split it into heads, right? You just like multiply by because the weight matrix. Do we just duplicate it after? One head, yeah. I believe. So it's like aged. Oh shit, is that X? Yeah, multi-head attention is just H by DK is this matrix. So this is for efficient implementation. And then this is just L. So when do we concatenate it? Because you have a all by dk for each head. Ungroup. Okay. Yeah, you divide by square root of dk. Oh god. That was a question I asked, like, learns to I think I got it now, right? So we do this, and then there's the MLP. Okay, like let's say okay. Okay, within a given head, okay, got it. So we linearly project, we take from an embedding matrix, we go through a head, the forward, and you can shoot the attention and do value, and then do back a weights times v. Well, that's if your key self.key is some weight matrix, self.key is head size. This is actually head size. Wait, where is the training where?
Distribution. Station. Okay, so having said all that, let's now take our self-attention knowledge and let's take it for a spin. Self-attention component into our network right now. I had to make one more change, which is that here in the generate, we have to make sure that our IDX that we feed into the model, a little bit of diagram here. I don't know if this is super clear. It's really just multiple attentions in parallel. So let's implement that. Fairly straightforward. If we want a multi-head attention, then we want multiple heads of self-attention running in parallel. So in PyTorch, we can do this by simply creating multiple heads. So however many heads you want, and then what's the head size of each. And then we run all of them in parallel into a list and simply concatenate all of the outputs. And we're concatenating over the channel dimension. So the way this looks now is we don't have just a single attention that has a head size of 32, because remember, n embed is 32. Instead of having one...
Like, perhaps this is not clear. I messed up. This needs to be longer, I think. But, do you really want to bother with this? Is this the best color? Like, probably not. I don't like the color. Okay. So these are the heads.
Communication channel. We now have 4 communication channels in parallel. And each one of these communication channels typically will be smaller correspondingly. So because we have 4 communication channels, we want 8-dimensional self-attention. And so from each
Yeah. For readability.
communication channel, we're going to together 8-dimensional vectors, and then we have 4 of them, and that concatenates to give us 32, which is the original n embed. And so this is kind of similar to, if you're familiar with convolutions, this is kind of like a group convolution, because basically, instead of having one large convolution, we do convolution in groups, and that's multi-headed self-attention. And so then here, we just use SA heads, self-attention heads instead. Now, I actually ran it, and scrolling down, I ran the same thing, and then we now get down to 2.28, roughly. And the output is still, the generation is still not amazing, but clearly the validation loss is improving because we were at 2.4 just now. And so it helps to have multiple communication channels because obviously these tokens have a lot to talk about. They want to find the consonants, the vowels, they want to find the vowels just from certain positions, they want to find any kinds of different things. And so it helps to create multiple independent channels of communication, gather lots of different types of data, and then decode the output. Now going back to the paper for a second, of course I didn't explain this figure in full detail, but we are starting to see some components of what we've already implemented. We have the positional encodings, the token encodings that add, we have the masked multi-headed attention implemented. Now here's another multi-headed attention, which is a cross attention to an encoder, which we're not going to implement in this case. I'm going to come back to that later. But I want you to notice that there's a feed-forward part here, and then this is grouped into a block that gets repeated again and again. Now the feed-forward part here is just a simple multi-layer perceptron. In full detail.
Forward.
But we are starting to see some components of what we've already implemented. We have the positional encodings, the token encodings that add, we have the masked multi-headed attention implemented. Now, here's another multi-headed attention, which is a cross attention to an encoder, which we're not going to implement in this case. I'm going to come back to that later. But I want you to notice that there's a feed-forward part here, and then this is grouped into a block that gets repeated again and again. Now, the feed-forward part here is just a simple multi-layer perceptron. So the multi-headed, so here position-wise feed-forward networks is just a simple little MLP. So I want to start basically in a similar fashion, also adding computation into the network. And this computation is on a per node level. So I've already implemented it, and you can see the diff highlighted on the left here when I've added or changed things. Now before we had the multi-headed self-attention that did the communication, but we went way too fast to calculate the logits. So the tokens looked at each other, but didn't really have a lot of time to think on what they found from the other tokens. And so what I've implemented here is a little feed-forward single layer. And this little layer is just a linear followed by a relu nonlinearity, and that's it. So it's just a little layer. And then I call it feed-forward. Attentions do individually. And so that's what feed-forward is doing, and that's why I've added 8. When it has blocks that communicate and then compute, and it groups them and replicates them. Okay, so let me show you what we'd like to do. We'd like to do something like this. We have a block, and this block is basically this part here, except for the cross-attention. Now the block basically intersperses communication and the computation. The communication is done using multi-headed self-attention, and then the computation is done using a feed-forward network on all the tokens independently. Now, what I've added here also is, you'll notice, this takes the number of embeddings in the embedding dimension and the number of heads that we would like, which is kind of like group size in group convolution. And I'm saying that the number of heads we like is 4, and so because this is 32, we calculate that because this is 32, the number of heads should be 4, the head size should be 8, so that everything sort of works out channel-wise. So this is how the transformer structures sort of the size.
It doesn't have to be.
Typically. So the head size will become 8, and then this is how we want to intersperse them. And then here, I'm trying to
It doesn't have to be.
Now the block basically intersperses communication and then computation. The communication is done using multi-headed self-attention, and then the computation is done using a feed-forward network on all the tokens independently. Now, what I've added here also is, you'll notice, this takes the number of embeddings in the embedding dimension and the number of heads that we would like, which is kind of like group sizing, group convolution. And I'm saying that the number of heads we like is 4, and so because this is 32, we calculate that because this is 32, the number of heads should be 4, the head size should be 8, so that everything sort of works out channel-wise. So this is how the transformer structures sort of the sizes, typically. So the head size will become 8, and then this is how we want to intersperse them. And then here, I'm trying to create blocks, which is just a sequential application of block, 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 so that we're interspersing communication feed-forward many, many times, and then finally we decode. Now, I actually tried to run this, and the problem is this doesn't actually give a very good answer, a very good result. And the reason for that is we're starting to actually get like a pretty deep neural net. And deep neural nets suffer from optimization issues, and I think that's what we're kind of like slightly starting to run into. So we need one more idea that we can borrow from the transformer paper to resolve those difficulties. Now, there are 2 optimizations that dramatically help with the depth of these networks and make sure that the networks remain optimizable. Let's talk about the first one. The first one in this diagram is, you see this arrow here, and then this arrow and this arrow. Those are skip connections, or sometimes called residual connections. They come from this paper, the Procedural Learning for Image Recognition, from about 2015, that introduced the concept. Now, these are basically, what it means is you transform the data, but then you have a skip connection with addition from the previous features. Now, the way I like to visualize it, that I prefer, is the following. Here the computation happens from the top to bottom, and basically you have this residual pathway. And you are free to fork off from the residual pathway, perform some computation, and then project back to the residual pathway via addition. And so you go from the inputs to the targets only via plus and plus and plus. And the reason this is useful is because during backpropagation, remember from our micrograd video earlier, addition distributes gradients equally to both of its branches that fed as the input. And so the supervision, or the gradients from the loss, basically hop through every addition node all the way to the input, and then also fork off into the residual blocks. But basically you have this gradient superhighway that goes directly from the supervision all the way to the input, unimpeded. And then these residual blocks are usually initialized in the beginning, so they contribute very, very little, if anything, to the residual pathway. They are initialized that way. So in the beginning, they are sort of almost kind of like not there. But then during the optimization, they come online over time, and they start to contribute. But at least at the initialization, you can go from directly supervision to the input. Gradient is unimpeded and just flows, and then the blocks over time kick in. And so that dramatically helps with the optimization. So let's implement this. So coming back to our block here, basically what we want to do is we want to do x equals x plus self-attention and x equals x plus self.feed forward. So this is x, and then we fork off and do some communication and come back. And we fork off and we do some computation and come back. So those are residual connections. And then swinging back up here, we also have to introduce this projection. So nn.linear. And this is going to be from, after we concatenate this is the size n embed. So this is the output of the self-attention itself. But then we actually want the to apply the projection, and that's the result. So the projection is just a linear transformation of the outcome of this layer. So that's the projection back into the residual pathway. And then here in the feed forward, it's going to be the same thing. I can have a self-out projection here as well. But
the thing is n embed. Do we? They can be arbitrary. One.
let me just simplify it, and let me couple it inside the same sequential container. And so this is the projection layer going back into the residual pathway. And so that's it. So now we can train this. So I implemented one more small change. When you look into the paper again, you see that the dimensionality of input and output is 512 for them. And they're saying that the inner layer here in the feedforward has a dimensionality of 2048. So there's a multiplier of 4. And so the inner layer of the feedforward network should be multiplied by 4 in terms of channel sizes. So I came here and I multiplied 4 times embed here for the feedforward, and then from 4 times n embed coming back down to n embed when we go back to the projection. So adding a bit of computation here and growing that layer that is in the residual block on the side of the residual pathway. And then I train computation here and growing that layer that is in the residual block on the side of the residual pathway. And then I train this, and we actually get down all the way to 2.08 validation loss. And we also see that the network is starting to get big enough that our train loss is getting ahead of validation loss. So we start to see like a little bit of overfitting. And our generations here are still not amazing, but at least you see that we can see like is here, this now, brief sync. Like this starts to almost look like English. So yeah, we're starting to really get there. Okay, and the second innovation that is very helpful for optimizing very deep neural networks is right here. So we have this addition now, that's the residual part. This norm is referring to something called layer norm. So layer norm is implemented in PyTorch. It's a paper that came out a while back here. And layer norm is very, very similar to batch norm. So remember back to our Make More series part 3. We implemented batch normalization. And batch normalization basically just makes sure that across the batch dimension, any individual neuron had unit Gaussian distribution. So it was 0 mean and unit standard deviation, 1 standard deviation output. So what I did here is I'm copy pasting the batch norm 1D that we developed in our Make More series. And see here we can initialize, for example, this module, and we can have a batch of 32 100-dimensional vectors feeding through the batch norm layer. So what this does is it guarantees that when we look at just the 0th column, it's a 0 mean, 1 standard deviation. So it's normalizing every single column of this input. Now the rows are not going to be normalized by default because we're just normalizing columns. So let's now implement layer norm. It's very complicated. Look, we come here, we change this from 0 to 1. So we don't normalize the columns, we normalize the rows. And now we've implemented layer norm. So now the columns are not going to be normalized, but the rows are going to be normalized. For every individual example, its 100-dimensional vector is normalized in this way. And because our computation now does not span across examples, we can delete all of this.
Should I hide the batch dimension? Do I even...
in this way. And because our computation now does not span across examples, we can delete all of this buffers stuff because we can always apply this operation and don't need to maintain any running buffers. So train layer norm in our have these before it goes into norm and then like a perkin. So for now, this is incorporating the layer norms, and let's train them up. Okay, so I let it run, and we see that we get down to 2.06, which is better than the previous 2.08. So a slight improvement by adding the layer norms. And I expect that they help even more if we have a bigger and deeper network. One more thing I forgot to add is that there should be a layer norm here also typically as at the end of the transformer and right before the final linear layer that decodes into vocabulary. So I added that as well. So at this stage, we actually have a pretty complete transformer according to the original paper, and it's a decoder-only transformer. I'll talk about that in a second.
But at this stage, the major pieces are in place, so we can try to scale this up and see how well we can push this number. Now, in order to scale up the model, I had to perform some cosmetic changes here to make it nicer. So I introduced this variable called nLayer, which just specifies how many layers of the blocks we're going to have. I created a bunch of blocks, and we have a new variable number of heads as well. I pulled out the layer norm here, and so this is identical. Now, one thing that I did briefly change is I added dropout. So dropout is something that you can add right before the residual connection back, or right before the connection back into the residual pathway. So we can drop out that as the last layer here. We can drop out here at the end of the multi-header transition as well. And we can also drop out here when we calculate the basically affinities, and after the softmax, we can drop out some of those. So we can randomly prevent some of the nodes from communicating. And so dropout comes from this paper from 2014 or so. And basically it takes your neural net, and it randomly, every forward-backward pass, shuts off some subset of neurons. So randomly drops them to 0 and trains without them. And what this does effectively is, because the mask of what's being dropped out is changed every single forward-backward pass, it ends up kind of training an ensemble of subnetworks. And then at this time, everything is fully enabled, and kind of all of those subnetworks are merged into a single ensemble, if you want to think about it that way. So I would read the paper to get the full detail. For now, we're just going to stay on the level of this is a regularization technique, and I added it because I'm about to scale up the model quite a bit, and I was concerned about overfitting. So now when we scroll up to the top, we'll see that I changed a number of hyperparameters here about our neural net. So I made the batch size be much larger, now it's 64. I changed the block size to be 256. So previously it was just 8 characters of context. Now it is 256 characters of context to predict the 257th. I brought down the learning rate a little bit because the neural net is now much bigger, so I brought down the learning rate. The embedding dimension is now 384, and there are 6 heads. So 384 divided 6 means that every head is 64 dimensional as a standard. And then there's going to be 6 layers of that. And the dropout will be at 0.2. So every forward-backward pass, 20% of all these intermediate calculations are disabled and dropped to 0. And then I already trained this and I ran it. So drum roll, how well does it perform? So let me just scroll up here. We get a validation loss of 1.48, which is actually quite a bit of an improvement on what we had before, which I think was 2.07. So we went from 2.07 all the way down to 1.48 just by scaling up this neural net with the code that we have. And this, of course, ran for a lot longer. This maybe trained for, I want to say, about 15 minutes on my A100 GPU, so that's a pretty good GPU. And if you don't have a GPU, you're not going to be able to reproduce this. On a CPU, this would be, I would not run this on a CPU or a MacBook or something like that. You'll have to break down the number of layers and the embedding dimension and so on. But in about 15 minutes, we can get this kind of a result. And I'm printing some of the Shakespeare here, but what I did also is I printed 10,000 characters, so a lot more, and I wrote them into a file. And so here we see some of the outputs. So it's a lot more recognizable as the input text file. So the input text file, just for reference, look like this. So there's always like someone speaking in this manner, and our predictions now take on that form. Except, of course, they're nonsensical when you actually read them. So that is, every crimty be house. Oh, those prepation. We give heed. You know, oh, sent me you, mighty lord. Anyway, so you can read through this. It's nonsensical, of course, but this is just a transformer trained on the character level for 1 million characters that come from Shakespeare. So it's sort of like blabbers on in Shakespeare-like manner, but it doesn't, of course, make sense at this scale. But I think still a pretty good demonstration of what's possible. So now, I think that kind of like concludes the programming section of this video. We basically kind of did a pretty good job in implementing this transformer, but the picture doesn't exactly match up to what we've done. So what's going on with all these additional parts here? So let me finish explaining this architecture and why it looks so funky. Basically what's happening here is, what we implemented here is a decoder-only transformer. So there's no component here. This part is called the encoder, and there's no cross-attention block here. Our block only has a self-attention and the feed-forward, so it is missing this third in-between piece here. This piece has cross-attention. So we don't have it, and we don't have the encoder, we just have the decoder. And the reason we have a decoder only is because we are just generating text, and it's unconditioned on anything. We're just blabbering on according to a given dataset. What makes it a decoder is that we are using the triangular mask in our transformer. So it has this autoregressive property where we can just go and sample from it. So the fact that it's using the triangular mask to mask out the attention makes it a decoder, and it can be used for language modeling. Now, the reason that the original paper had an encoder-decoder architecture is because it is a machine translation paper. So it is concerned with a different setting. In particular, it expects some tokens that encode, say, for example, French, and then it is expected to decode the translation in English. So you typically, these here are special tokens. So you are expected to read in this and condition on it. And then you start off the generation with a special token called start. So this is a special new token that you introduce and always place in the beginning. And then the network is expected to output neural networks are awesome, and then a special end token to finish the generation. So this part here will be decoded exactly as we've done it. Neural networks are awesome, will be identical to what we did. But unlike what we did, they want to condition the generation on some additional information. And in that case, this additional information is the French sentence that they should be translating. So what they do now is they bring the encoder. Now the encoder reads this part here. So we're only going to take the part of French, and we're going to create tokens from it exactly as we've seen in our video. What happens is all the boilerplate code for training the network. It is basically all the stuff that we had here is the training loop. It's just that it's a lot more complicated because we are saving and loading checkpoints and pre-trained weights, and we are decaying the learning rate and compiling the model and using distributed training across multiple nodes or GPUs. So the training.py gets a little bit more hairy, training the network, which is outside on, and then decoder only transform. T is basically 2 files of interest. There's train.py and model.py. Train.py is all the boilerplate code for training the network. It is basically all the stuff that we had here is the training loop. It's just that it's a lot more complicated because we're saving and loading checkpoints and pre-trained weights, and we are decaying the learning rate and compiling the model and using distributed training across multiple nodes or GPUs. So the train.py gets a little bit more hairy, complicated. There's more options, etc. But the model.py should look very, very similar to what we've done here. In fact, the model is almost identical. So first, here we have the causal self-attention block, and all of this should look very, very recognizable to you. We're producing queries, keys, values, we're doing dot products, we're masking, applying softmax, optionally dropping out, and here we are pooling the values. What is different here is that in our code, I have separated out the multi-headed attention into just a single individual head, and then here I have multiple heads and I explicitly concatenate them. Whereas here, all of it is implemented in a batched manner inside a single causal self-attention. And so we don't just have a B and a T and a C dimension, we also end up with a fourth dimension, which is the heads. And so it just gets a lot more sort of hairy because we have four-dimensional array tensors now, but it is equivalent mathematically. So the exact same thing is happening as what we have. It's just it's a bit more efficient because all the heads are now treated as a batch dimension as well. Then we have the multilayer perceptron. It's using the Gaussian nonlinearity, which is defined here instead of Rayleigh. And this is done just because OpenAI used it and I want to be able to load their templates. The blocks of the transformer are identical. They communicate in the compute phase, as we saw. And then the GPT will be identical. We have the position encodings, token encodings, the blocks, the layer norm at the end, the final linear layer. And this should look all very recognizable, identical. I used it. Equivalent multilayer perceptron dimension, which is the heads, is implemented in a batched manner inside a single causal self-attention. And so we don't just have a B and a T and a C dimension. We also end up with a fourth dimension, which is the heads. And so it just gets a lot more sort of hairy because we have four-dimensional array tensors now, but it is equivalent mathematically. The blocks of the transformer are identical. They communicate in the compute phase, as we saw. And then the GPT will be identical. We have the position encodings, token encodings, the blocks, the layer norm at the end.
I guess it's misleading. Sure. I'm confused about the shapes. Interesting.
The final linear layer. And this should look all very recognizable. And there's a bit more here because I'm loading checkpoints and stuff like that. I'm separating out the parameters into those that should be weight decayed and those that shouldn't. But the generate function should also be very, very similar. So a few details are different, but you should definitely be able to look at this file and be able to understand a lot of the pieces now. So let's now bring things back to ChatGPT. What would it look like if we want to train ChatGPT ourselves, and how does it relate to what we learned today? Well, to train ChatGPT, there are roughly two stages. First is the pre-training stage, and then the fine-tuning stage. In the pre-training stage, we are training on a large chunk of internet and just trying to get a first decoder-only transformer to babble text. So it's very, very simple. They are training a significantly larger model on a good chunk of the internet, and that is the pre-training stage. But otherwise, these hyperparameters should be fairly recognizable to you. So GP, you get babble Shakespeare, it babble responds to your questions with answers, and it's not helpful, and etc. You get a document completer, right? So it babbles, but it doesn't babble Shakespeare, it babbles internet. It will create arbitrary news articles and documents, and it will try to complete documents because that's what it's trained for. It's trying to complete the sequence. So when you give it a question, it would just potentially just give you more questions. It would follow with more questions. It will do whatever it looks like some closed document would do in the training data on the internet. And so who knows, you're getting kind of like undefined behavior. It might basically answer to questions with align it to be an assistant. And this is the second stage. And so this ChatGPT blog post from OpenAI talks a little bit about how this stage is achieved. We basically there's roughly 3 steps to this stage, and they then fine-tune the model. And these very, very large models are very sample efficient during their fine-tuning, so this actually somewhat works. But that's just step 1, that's just fine-tuning. So then they actually have more steps where, okay, the second step is you let the model respond, and then different raters look at the different responses and rank them for their preferences to which one is better than the other. They use that to train a reward model, so they can predict, basically using a different network, how much of any candidate response would be desired, this sampling policy, so that the answers that the ChatGPT now generates are expected to score a high reward according to the reward model. And so basically there's a whole aligning stage here, or fine-tuning stage. It's got multiple steps in between there as well. And it takes the model from being a document completer to a question answerer. And that's like a whole separate stage. A lot of this data is not available publicly. It is internal to OpenAI, and it's much harder to replicate this stage. And so that's roughly what we do at ChatGPT. And NanoGPT focuses on the pre-training stage. Okay, and that's everything that I wanted to cover today. So we trained, to summarize, a decoder-only transformer following this famous paper, Attention is All You Need, from 2017. And so that's basically a GPT. We trained it on a tiny Shakespeare and got sensible results. All of the training code is roughly 200 lines of code. I will be releasing this code base. So also it comes with all the GitLog commits along the way as we built it up. In addition to this code, I'm going to release the notebook, of course, the Google Colab. And I hope that gives you a sense for how you can train these models, like say GPT-3, that will be architecturally basically identical to what we have, but they are somewhere between 10,000 and 1 million times bigger, depending on how you count. And so that's all I have for now. We did not talk about any of the fine-tuning stages, and typically go on top of this. So if you're interested in something that's not just language modeling, but you actually want to say perform tasks, or you want them to be aligned in a specific way, or you want to detect sentiment or anything like that, basically anytime you don't want something that's just a document completer, you have to complete further stages of fine-tuning, which we did not cover. And that can be simple supervised fine-tuning, or it can be something more fancy like we see in ChatGPT, where you actually train a reward model and then do runs of PBO to align it with respect to the reward model. So there's a lot more that can be done on top of it. I think for now we're starting to get to about 2 hours mark, so I'm going to kind of finish here. I hope you enjoyed the lecture, and yeah, go forth and transform. See you later. Model has not seen during training, and we see that we go from doing the task not very well, because we're initializing from scratch, all the way to doing the task quite well by the tensor solve that file. And by the way, here this is a Jupyter node. So the first thing I would like to do is actually start at the end, or at the target. So in other words, let's load the GPT-2 124M model as it was released by OpenAI, and maybe take the first spin. Let's sample some tokens from it. Now the issue with that is when you go to the code base of GPT-2 and you go into the source and you click in on the model.py, you'll realize that actually this is using TensorFlow. So the original GPT-2 code here was written in TensorFlow, which is not, let's just say, not used as much anymore. So we like to use PyTorch because it's a lot friendlier, easier, and I just personally like it a lot more. The problem with that is the initial code is in TensorFlow. We like to use PyTorch. So instead, to get the target, we're going to use that. Okay, so as we can see, we are currently at about 300 milliseconds per iteration, and we're now going to reach for some really heavy weapons in the PyTorch arsenal. In particular, we're going to introduce torch.compile. So torch.compile is really quite incredible infrastructure from the PyTorch team, and it's basically a compiler. So torch.compile is really quite incredible infrastructure from the particular team, and it's basically a compiler for neural networks. Like, it's almost like GCC for C and C++ code, and this is just the GCC of neural nets. So it came out a while ago and extremely simple to use. The way to use torch compile. Now this let me run that, because this will take some time to run, but currently remember we're at 300 milliseconds to not use torch compile in your PyTorch. I kind of feel like you should be using it almost by default if you're not, unless you're debugging and you want your code to run really fast. And there's one line here in torch compile that I found that actually kind of like gets to why this is faster. Speed up mainly comes from reducing Python overhead and GPU read writes. So let me unpack that a little bit. Okay, here we are. Okay, so we went from 300 milliseconds, we're now running at 129 milliseconds. So this is 300 divided by 129, about 2.3x improvement from a single line of code in PyTorch. So quite incredible. So what is happening? What's happening under the hood? Well, when you pass the model to torch compile, what we have here in this NN module, this is really just the algorithmic description of what we'd like to happen. And then it printed, so process 5 basically got here first.
Where goes your GDP?
Electronics. TF32 is the exact, it's even more aggressive in cropping off of the precision, the mantissa of this float. So the important thing, I'd like to get to training, and I'd like to start training the model. And for now, let's just say the device makes code go fast. And let's go into how we can actually train the model. So to train the model, we're going to need some data set. And for me, the best debugging, simplest dataset that I like to use is the Tiny Shakespeare dataset. And it's available at this URL, so you can get it, or you can just search Tiny Shakespeare dataset. And so I have it in my file system as just lsinput.txt. So I already downloaded it. And here,
We really should do it on someone.
in particular, today we are going to reproduce the GPT-2 model. Okay, so now we're going to try to set up the identical thing on the left here that matches Hugging Face on the right. So here we've sampled from the pipeline, and we sampled 5 times up to 30 tokens with the prefix of hello, I'm a language model, and these are the completions that we achieved. So we're going to try to replicate that on the left here. So number
Okay, I'm gonna wrap it up here. Yeah, probably gonna think of like a small project to do this stuff, so I get better at modeling. And working with text is much easier than working with robotics data, and if you can train a model, and it works, sort of helps you get a good intuition of what's happening. Alright, I'll see you hopefully tomorrow.